calorimetry refers to the measurement of heat flow. And in this worked example, we're going to burn a marshmallow and find the energy content of the marshmallow. First, let's look at the setup for our soda can calorimeter. So our soda can has some water in it. So here's the water in our soda can. And then we also have a thermometer in the soda can to measure the change in the temperature of the water. If you take a stir rod and you put the stir rod through the tab on the soda can, you can attach the soda can to a stand. Next, we can put our marshmallow on a pin that's attached to a piece of cork. Before we start the experiment, we need to take the mass of the marshmallow with the cork and the pin, so we'll call that the initial mass. And we also need the initial temperature of the water, so we'll call that T sub I. Next, we light the marshmallow on fire. As the marshmallow burns, heat is given off, and that heat is transferred to the water in the soda can. Therefore, the water in the soda can will increase in temperature, which we can see on the thermometer. After the marshmallow burns for a little while, we can stop the burning process. And once we stop that, we want to look at the thermometer for the maximum temperature reached. And when we find that maximum temperature, we can go ahead and record it. So we have a final temperature. And once the marshmallow with the cork and the pin cools down, we can find a final mass. Let's say the initial mass of our marshmallow pin cork was 6.08 grams, and the final mass was 6.00 grams. The initial temperature of the water in the soda can was 25.0 degrees Celsius, and the final temperature was 30.0 degrees Celsius. Also, let's say that we started with 50.0 grams of water in the soda can. Let's calculate the heat gained by the water. To do that, we can use the Q is equal to mc delta T equation, where Q is equal to the heat transferred. M is the mass of the water, which is 50.0 grams. C is the specific heat of water, which is 4.18 joules per gram degree Celsius. And delta T is the change in temperature, which would be the final temperature minus the initial temperature of the water, which is 30.0 minus 25.0, which is equal to 5.0 degrees Celsius. Grams cancels out, degrees Celsius cancels out, and we find that Q is equal to positive 1.0 times 10 to the third joules. That's to two significant figures. The positive sign here means that heat was gained by the water, which is why we saw an increase in the temperature. If we assume a perfect transfer of heat, so all the heat that was given off by the burning of the marshmallow was transferred to the water, if we think about Q for the burning of the marshmallow, it should be equal in magnitude. So we can write Q is equal to, this time we're going to write a negative, since heat was given off by the burning of the marshmallow, 1.0 times 10 to the third joules. So assuming a perfect transfer of heat, the magnitude of these two numbers is equal. However, there's no way that all of the heat was transferred from the combustion of the marshmallow to the soda can with our simple setup. So definitely not all of it was transferred. For example, some of it could have been lost simply to the environment. And since this soda can is open to the atmospheric pressure of the environment, so I'll go ahead and write atmospheric pressure in here, this soda can calorimeter is an example of constant pressure calorimetry. And since this is the heat that's transferred under constant pressure, I can go ahead and write QP here to indicate the heat transferred under constant pressure. That's the definition of the change in enthalpy delta H. So burning the marshmallow gave off energy, which is an exothermic reaction. Therefore, the sign for delta H is negative. Finally, let's relate this soda can calorimetry experiment to calories in everyday life. And so let's find the energy content of the marshmallow in calories per gram. A food calorie has a capital C, And in chemistry, there's also a unit of energy with calorie with a lowercase c. So one food calorie with a capital C is equal to 1 kilocalorie or 1,000 calories with a lowercase c. When we burned the marshmallow, we started off with a mass of 6.08 grams for the marshmallow pin cork, and the final mass was 6.00 grams, which means we burned 0.08 grams of marshmallows. When we burned the marshmallow, we found there was a transfer of 1.0 times 10 to the third joules of energy. So first, let's convert that into calories with a lowercase c. So if we multiply by the conversion factor of there's 1 calorie with a lowercase c for every 4.184 joules, joules will cancel out, and this gives us 239 calories with a lowercase c. Next, let's convert 239 calories into food calories. So first, let's take 239 calories, and we can multiply by the conversion factor of there are 1,000 calories with a lowercase c for every 1 kilocalorie, and that's going to give us 0.239 kilocalories. And going back up here to our chart, remember, 1 kilocalorie is equal to 1 food calorie with a capital C. Therefore, we have 0.239 kilocalories or 0.239 calories with a capital C, which is a food calorie. To find the energy content of the marshmallow in calories per gram, we just need to divide our food calories by how many grams of marshmallows we use, which was 0.08 grams in our combustion. So dividing by 0.08 grams gives us approximately 3 calories per gram of marshmallows. And that's useful because let's say we had 1 serving size of marshmallows, which is about 30 grams. So therefore, if we know the energy content is 3 calories per gram, we can simply multiply our 4 marshmallows, approximately, by 3 calories per gram, and grams would cancel out, and we would find that those 4 marshmallows that we wanted to eat are about 90 food calories.